Hi, welcome to educator.com. Today we're going to be talking about sampling distribution of sample proportions. All right, so first thing we're going to do is just introduce ourselves to the concept of sampling distribution of sample proportions. And this is just me, this is not like everybody in statistics, but I'm just going to call it SDOSP for short, so that we don't have to keep writing out sampling distribution of sample proportions. Then we're going to go through some notation. And then finally, we're going to compare and contrast the SDOSP right here to the SDOM. They're both sampling distributions, but one is of the mean and the other is of sample proportions. Then we're going to compare and contrast the binomial distribution, the probability distribution that we looked at a couple lessons back, with the SDOSP. All right, so first, what is this thing? What is the SDOSP? Well, first, this concept is going to come into play whenever we collect some sort of categorical data. For instance, we might ask a sample of citizens, do you approve or disapprove of the president? And that would be a categorical response. They're not saying, I approve this much, but they're just saying, I approve or disapprove. So then, at the end of that data collection, what you get is not a mean or a median, but you get something like a proportion of citizens who believe the president is doing a good job. Something like 43%, 64%, 29%, right? Or another example might be proportion of students who have plagiarized on a paper before. So here we're getting proportions, right? They're not means or medians, they're just percentages of the entire sample. And finally, another one that's been talked about a lot these days is the proportion of people covered under healthcare. So when we collect this categorical data, oftentimes we want to use that in order to estimate the proportion of the population that actually is covered by healthcare or who have plagiarized before or who believe the president is doing a good job. We want to estimate that population level parameter. However, samples are very variable, right? So samples are variable. And that means that our estimate won't always be very good. It'll be good sometimes, but it won't always be very good. So it would really help us out if we knew the entire distribution of potential samples, right? Wouldn't that be handy? And that is called a sampling distribution. And because we're not sampling and finding a mean, instead we're sampling and finding a proportion, it's called a sampling distribution of sample proportions, right? And so this is the idea found here, the entire distribution of potential samples. But once we get each sample, what do we do to it? We don't find the mean, we find the sample proportion. And then we plot those on a distribution. All right, so some things that are helpful for us to get straight. So when we talk about the population proportion, that parameter, we'll just call it P, lowercase p. But when we talk about a sample proportion, we're going to call it p hat, right? And we've seen that notation before when we talked about regression, when we had y for the actual data, but we had y hat for the predicted data. You could sort of think about it like this. The real one, right? The real one from the world is going to be not have the hat, right? So this is sort of the truth that we're trying to find, right? And this is how we're going to estimate that truth. So we're going to use this to estimate that. But we want to know, how good is our estimate? Is it any good? Is it reliable? Is it not? And so you could think about it like this. Here, the distribution of the population is binary. There's one or the other, right? So I'm just going to draw the entire population as just a bar and pretend this bar has the value of 1.0, 100%, right? Some proportion of this is P, and the other is not P. So some proportion of these people approve of the president's job, approve of the job he's doing as president, and the other half, the other proportion does not, right? How should we represent that in sort of picture and algebraic form? Well, I'm just going to draw a line here and say this part is going to be my proportion P. That is my proportion of those that agree that the president is doing a good job, let's say, right? Then what would be this, this little area here? How would we represent that algebraically? Well, that would simply be 1 minus P, right? Because the whole thing is P, this segment is P, so this segment must be 1 minus P, right? And so when you add P plus 1 minus P, what you get is 1, right? And notice that we didn't draw like a normal distribution or anything, because it's not that people have different values, right? It's not that some people are low, some people are high. It's just yes or no. Do you, have you plagiarized or not? Have you gone bungee jumping or not? Are you covered by healthcare or not, right? So they're just these binary characteristics that we're interested in. So that's what the population is like. Now from this population, we draw a sample of size n. Draw a sample size n, right? Just like always, right? So we're always drawing samples of size n. Now, when we look at that little sample of this population, right, what does it look like? So instead of the whole thing, you drew a little sample. You drew a subset of those people, right? And presumably, this little sample should most likely reflect the population that it came from, right? So this shouldn't be radically different from this. It can be sometimes, but for the most part, this sample should reflect the population that it came from. So, you know, in the sample, we'll have, so the entire sample, now this little thing equals 1. And in this entire sample, we have some probability, p hat, right? And those are the people, that's the proportion in our sample that agree, let's say. And this would be represented by 1 minus p hat. Those are the people in our sample that disagree. Now you might be thinking, how is this whole thing 1 and how is this whole thing 1? Because this one looks smaller, right? Well, when we say 1, we're talking about proportions. So we're really saying 100%. So when we're saying 1 here, it represents 100% of the population. When we say 1 down here, we are saying 100% of the sample, right? So that's the distinction we want to make. Now, once you do this, then you get this p hat, right? And once you have that p hat, then you could plot it on a distribution, on a sampling distribution. So here's what the sampling distribution of sample proportions looks like. The lower bound and upper bound on this have to be 0 and 1. You can never have a p hat that's less than 0. And you can never have a p hat that's greater than 100%. So you're inevitably stuck between 0 and 1. Those are the only sample proportions you could possibly get. Whatever we get here, we plot here. We plot that here, we plot that here. And soon we'll build up a sampling distribution of sample proportions, right? And whatever it looks like, that will be our sampling distribution of sample proportions. All right, so now let's contrast the SDOM versus the SDOSP. And in fact, we are going to learn more about the SDOSP by learning about the SDOM and how it relates. So there's one key difference between these two, and that's the biggest thing you really need to keep in mind. When we're talking about the SDOM, we're finding a mean. You can't find a mean between agree and disagree, right? Those are categorical data. So here, what we do is we need the data where you can find the mean. And those data are continuous data. Sometimes these are also called measurement data, because you actually got this by measuring something. So when you have continuous data, for instance, how many miles do you drive per day, right? So getting a sample of, what's the average number of miles people in California drive, right, each day. So that would be a continuous measure. If you get data like that, you could actually average it together. But if we ask a question like, do you drive every day, yes or no, right, that would be categorical data, right? And the type of data we're talking about here happens to be binary, because it's either you're in one category or you're in the other. There's not like three categories, right? So it's like there might be you agree with the president, you disagree with the president, or you feel neutral, right? But what we would do in order to look at an SDOSP is to sort of lump people together. So it might be agree versus disagree, don't care, right? So we might lump those two people together to just call them not agrees. All right, so the shape of the SDOM, what's nice about it is that as n increases, what happens to the shape? Shape approaches or approximates normal. So as our sample size increases, the shape is more and more reliably normal. The nice thing about the SDOSP is that the same principle applies. So you could just draw a little link there, right? As n increases, shape approximates normal. Because as we draw sample sizes of size n, as n gets bigger, even for SDOSP, we're actually seeing normal-like distributions. And now let's talk about center, right? So if you remember the central limit theorem, that's where the shape, center, and spread stuff comes from. Center, if you remember, the mu, the population mu, equals the center of the SDOM, which is mu sub x bar. Remember, it's a whole bunch of little x bars, right? Now, there's sort of a similar idea here, but there is a difference. So basically, when we talk about center here, remember that we don't have a population mu. We don't have a population mean, right? Instead, what we have is something more like a population proportion. So we have that P, right? We have that P. And we want to know sort of the relationship between P and P hat, right? And so in this case, what we see is that the mu that we want to see is going to be equal to this proportion. And if you think about it, it just sort of goes like this. Let's say you have 60% of your population as approving of the president, right? 60%. If you draw just one person from that population, what's the chance that that one person approves of the president? And that one person has a 60% chance of approving the president, right? And when you draw two people, those two people also have a 60% chance of approving of the president. And if you draw three people, they still have a 60% chance of approving of the president, right? And so really, the population P is equal to the mu, because remember, now we have a mean because we have a distribution of P hats, right? So here's the idea. get all these p hats, the entire distribution of p hats. Once you have those, if you find the mean of that, that is equal to the population, right? So that's the nice thing about this center. And remember, this number is between 0 and 1 because you can't have lower than 0, higher than 1. But so is this value. This value is also between 0 and 1, right? Another way you could think about it is that the rate in the population will be the rate that you eventually get, will be the mean of all the rates, right, that you get in your samples. Okay, so now let's talk about spread. When we talked about spread before, we often looked at standard deviation, right? Obviously, you could also look at variance and just square root both sides to get standard deviation. So here, when we talked about standard deviation of the SDOM, we called it sigma sub x bar because it's the standard deviation of a bunch of x bars, a bunch of means, right? And that is equal to sigma, the real population standard deviation, divided by the square root of n, so your sample size. So here, as n increases, what happens to the standard error? Oh, we should also call it standard error. What happens to standard error? Standard error goes down. So decreases, right? So as n goes up, standard error goes down. Because as n gets bigger and bigger and bigger, this whole thing gets smaller and smaller and smaller. All right. Now let's talk about the spread in the SDOSP. Here, remember, again, just like here, we didn't have a population mean. We don't have a population standard deviation. There's no, sort of variability there, right? And so instead, we use a different formula. So first, let's talk about variance here. In order to write variance, you call it sigma, and instead of sigma sub x bar, you call it sigma sub p hat, right? Just like mu sub p hat. You're constantly saying this is the sigma of a whole bunch of sample proportions, right? And because we're talking about variance, you want to square that. And that's going to also be the square root, oh wait, not square root yet. We're talking about variance, sorry. So that's going to be p times 1 minus p, all divided by n. And when you look at this, you see that this still holds for both of these, right? As n increases, what happens to the value of the spread? Spread goes down. So as n increases, spread goes down. So I imagine it coming sort of in, right? So it's squishing it, right? And so if you wanted to find standard deviation, what you would see is sigma sub p hat equals the square root of p times 1 minus p over n. Now, we'll talk a little bit more about where this comes from in the next segment. But what I really want you to see here is that there's this principle as n increases, as your sample size increases, your sampling distribution, doesn't matter of what, your sampling distribution's spread goes down. So it becomes less variable. All right. So we see a lot of sort of similarities across the SDOM and the SDOSP, excuse me.